Bien, le damos la bienvenida con un fuerte aplauso a José Luiz Oliveira.
Is it working? Oh, okay, it's working. I'll wait for the people to get there. Okay, I think you can start. Can I start? Okay. Hello, my name is José Oliveira. I'm going to be presenting Exec ASLR. We're going to be using Intel branch predictors to bypass ASLR. Well, first I'll do an introduction. What is ASLR? It's the acronyms for address space layout randomization. So basically, when you have a program, you compile it, and on the first execution, it changes the address of the functions that you are running. This is a mitigation to prevent attacks of memory corruption. So in this talk, we're going to present a way to bypass ASLR in, I believe, almost any case, if you have a big enough program. So I'm José Oliveira. I'm a cybersecurity consultant at Pride Security. I'm also a former CTF player on the Epicality team. I'm a member of a security incident response group at Federal University of Rio de Janeiro, and I'm also finishing my graduation at the same university. That is my Twitter. You can find me there if you have any questions later on, or if you want to talk about something about this talk. So about our agenda. We're going to be talking about, this is going to mainly be a review of some core concepts of computer architectures. We'll talk about CPU pipelines, then move on to branch predictors, take a look with some examples of side channel attacks. We're going to review Spectre attacks too, because this is actually a Spectre attack. We're going to review some other papers that do similar stuff. We have Jump Over ASLR. And then finally, we're going to present our novel attack, Exec ASLR, that allows full ASLR bypass and is fast and has few requirements to execute it. This is also a 0-day, okay? Well, let's talk about pipeline. What's the idea of a pipeline? Let's take, for example, a restaurant. If you have only one people working in a restaurant, well, usually it takes one client, takes the order, moves to the kitchen, then starts to prepare the meal, and then goes there to serve the other people. When you have a pipeline, it allows to do parallel production of something. So we have a waiter that goes there, takes the order, and moves on to the kitchen that prepares the meal, and then other guy goes there and delivers the food. So we divide the task in multiple stages that allows to better efficiency of the tasking. But we have a challenge when working with pipelines, is that usually the work that you are doing doesn't depend on the previous work that was done. For example, we don't have a workload dependency. So this was the schema that I talked about. We have a waiter that takes the order, then moves to the cashier that would decode the order and send to the kitchen, for example. And finally, the chef is going to cook the meal. So, for example, when we have a full restaurant, at most times, for example, on the cycle 3 there, there's going to be 3 people working at the same time. So they can finally work at a much more rate if there was only one people working on. Wait, we're going to get into the CPUs. This is just an analogy for that. What's the problem? Usually, when you are at a restaurant, no one goes there and order a conditional meal. For example, if a guy enters the restaurant and say, well, if that client there ordered a beef, a steak. If that steak comes burnt, I want a beer. Order, I want a spaghetti. Well, what the waiter should do now? Should it wait for the steak to get ready and check if it's burnt or not? That's a possibility, but it also takes longer for the whole meal to get prepared. So the waiter can do something like, for example, well, I know the steak will come okay, so I will already start doing the spaghetti, and then I can deliver both meals at the same time, and that will be much faster than just waiting for the steak to get done. But what if the steak gets burned in the process? Well, then I must throw the spaghetti out on trash and deliver the beer for the guy that requested it. That's what I call a speculative waiter. It's going to try to predict what's going to happen with the meal that gets requested and acting accordingly. So it will send the spaghetti order to the kitchen. And for example, here is an example that, well, the chef is also, it has to cook the steak and check if it's okay. And then at the same time, the spaghetti can also be cooking. So we have like two things doing at the same time. But one of that is not exactly sure if it's going to be used later. And well, let's make the following scenario. I'm also an attacker that I want to know, for example, if the waiter cooked the spaghetti by accident or not. I can order a spaghetti, and I will check the time. For example, I know that spaghetti usually takes 30 minutes to be ready. But if it took 15 minutes, I know that, for example, the ingredients must be moved out from the fridge and that the spaghetti will come earlier. So I can kind of infer if the waiter mispredicted the meal. So this is a kind of analogy for how this modern CPU works. Here we have an example of a fetch unit and the code and the execute unit. The fetch will be responsible for taking the instructions from the main memory, that, remember, is usually slow. The code will decode them in a nice way that the execution unit can understand, and the execution units will just run the actual instructions. So, for example, we have here a jump not zero instruction, the blue one. The fetch unit right now, it needs to take a decision. Because the fetch units don't know the exact value of the flag registers right here. It depends on the execution of the orange one instruction that's added there. So it must already know what the next instruction is. So it will make a speculation that's on the purple. And later, that speculation must be checked if it was correct or not. And if it was, it's OK. You can move on to the execution flow. Otherwise, you need to discard all the values that you get from the executing the wrong instruction. And for example, right here, we have the orange instruction taking a long of time because it uses memory, for example. At the same time, that I'm executing the purple one. That maybe should never be executed before. The only problem is that the processor cannot discard the effects of the purple execution exactly. Well, it can obviously not use the value written on DL, but for example, the RDX pointer there is going to be moved on to the cache. And that is a pretty perceptible change for an attacker. OK, that previous CPU was a simplification. This one is much more accurate. I took the image from the meltdown paper. You can take a look at that. It has a fetch unit, just like before. It has a decode unit, a queue for instructions, and they do a pretty smart thing that is instruction reordering. So the modern CPUs, they execute instructions out of order. For example, well, back into the kitchen analogy. for example, if some guy orders, for example, a salad, but he's on the end of the kiwi, but all the stoves are being used right now because they're cooking food. The chef can take the request from the last guy and start making the salad because the other units are occupied. So that's just that's similar what a CPU does. Instruction reordering. And then finally, we have a scheduling execution. We already saw that. So let's talk about branch prediction. That is, what should I do when I don't know what the next instruction going to be? The front end of the CPU. The front end of the CPU sometimes don't know what's the next instruction they should fetch. Well, for example, when you have a call like that one, when you have an indirect pointer right there on the RDI, there's going to be a special cache-like structure inside the CPU that helps the front end of the CPU to predict what the next instruction is going to be. So, for example, after executing the call, the CPU does a hash with the address and also the history of the last branches. That's not important right now. We're going to see later how it works. And then it queries this cache-like structure to know what's the predicted address right there. So the idea is that if I have a call in that place, the next call on that place will also be to the same value. So this is the mechanism that it uses to do this kind of predictions, at least on this type of instructions, the indirect calls and jumps. This is actually the mechanism that works for computing these previous tags. Right here, this is the tag that is going to be used, and here, oops, and here is the mechanism for doing that kind of prediction. You're going to ignore the direct branch predictor right now. We're going to only take a look to the indirect one. Forget that I don't have, I have here. Where it is, forget this thing here. We're only going to take a look at these two ones here. So first we have a branch history buffer that is kind of taking a hash of the last executed instructions that change for control flow. For example, a for loop writes on the branch history buffer. And that generates a hash using also the source address. And when I first took a look at this diagram, I saw a very interesting thing. Right here, we have a component that, where's the pointer, that predicts to a full address of 64 bits, but only uses 12 less significant bits as an entry for this thing. And right here, if you're going to take a look, it only uses 4 to 19. So basically, it's a component that takes the first 20 bits as entry and predicts to the full 64-bit address. And I was thinking, well, this may be a mechanism for breaking ASLR. This other predictor here, it's used, for example, in instructions that do not make a memory reference. For example, call array_x right there. No, the first one. Where it is? Oh, right here, this one. Yeah, there was another paper that used this predictor to also crack ASLR, but it only discovers the first half of the address because the address is predicted to the 32-bit destinations only. So this one can leak the entire address. So let's then take a look at side channel attacks. How do I discover the microarchitectural states of the stuffs when the CPU is speculating? So we have this this is inside a function there that's called a probe and receives an address. And it does a thing called a flush reload attack that discovers if an address is present on cache or if it's only on main memory. It does this by checking the time that it took to access that address. Right there we have a read TSC. Read TSC, it's the read timestamp counter. It's an instruction that takes the internal clock of the CPU that gets updated each clock cycle, and moves to another register that you can use it later. We also have the read of the pointer there. Then we read the internal clock again, and we use an instruction called CL flush that allows us to evict a cache line from the cache. Well, so it basically, after this read, the data is no longer on the cache. The mFence and LFence instructions are just because, as I said before, the CPU likes to reorder instructions of your code, and sometimes these effects can be noticeable. For example, the CPU can take the last instruction for reading the clock and move on to the first, and then I get a negative value. It looks insane. Yeah, so this is how I check the time that the address takes to get from the memory to the CPU. And if you plot that into a graph, that is my CPU. And what I did, I took the function from the last slide, and half of the times I try to probe the time of a cached value that are on the green, and half of the time trying to probe an address that was not cached. And you can see that it's a pretty significant difference. And well, you as attacker, if you want to discover if a data is present only on the main memory, you could draw a threshold here in the middle, there, and you say, well, below that everything is on cache. Above that, it's present on the main memory. So that's how you discover if a data is cached on the CPU or not. Well, this is a Spectre V1 example that I did as a challenge for Pontwin 2021. Well, okay, I'll give us some time to read this. Okay, understand what is going to happen here. We have two flags. The first one is kind of trivial to get it. The other one, not so much. And we receive a X value coming from the network. Well, the attacker has control over the X value. So right here, we do some arithmetic with this, and we're basically getting, well, what bit of the flag do you want? And I'm selecting that bit that you want and checking. Well, the bit is 1. If the bit is 1, I call getEnv. If the bit is 0, I don't do nothing. In this challenge, an attacker can execute code on the same computer, but he cannot interact more than just sending the X value. So how can it leak the entire flag? The idea is, for the first part, right here, that's what the exploit looks like. For the first part, I'll move back to here. For the first part, you don't need to do nothing special with this bound check. This bound check will always return true for the first flag, and this will get evaluated. The idea is, if a process running on the same core executes the getEnv function that's present on the libc, the other process that's also running on the same core, not exactly on the same core, it can be on the other core for this part, the execution of the other process also gets faster. So if this program here runs getEnv and then me as attacker run getEnv, I know that by the time it took to execute it, that the bit was 1. And then I can leak the first part of the flag. The idea of a Spectre V1 is that I can manipulate the CPU in order to do funny things with the execution flow. For example, right here we have a conditional instruction. We learned that conditional instructions, they tend to be speculated by the CPU. So there's a special kind of predictor that's what's not shown on the previous slide, but right here, if we set this branch here to execute multiple times, the CPU will believe that the next time it needs to go to that branch, it will also be executed. So what you can do, you can pass offset the X value here, 0, 0, 0, 0, 0. This guy is executing. These instructions are executing. And then you go to like 100. It should not execute, but will execute because the CPU is trained for executing that branch. And that's how you bypass this bound check and get the value of the flag. That's what I do here. I send like a 333 multiple times. Then I have this evict that we'll talk about later. Then we send the actual bit that I want to read from the flag. And then I do a flush reload attack that uses that probe function there. And then I can leak the entire flag. Well, let's move on to the version 2 of the attack. These attacks, they are pretty old. They're from like 2018, I think. But many new versions of the exploits are being discovered nowadays. So what's the idea of a Spectre V2? We have to meet some requirements. They need to both programs need to execute on the same context. On the same core. That can be, for example, a hyper thread thing. And have a context A executing on thread 0 and context B on thread 1. And they need to find a branch target buffer collision. The branch target buffer collision is what I was saying with the slides there in the beginning, that we need to make that hash function collide this thing here. And then I can do a funny stuff. For example, context B, that in this case is a legitimate user, is calling a function. But context A is also calling a function, and they are in a similar address right here. And the context B then will mispredict to the address set by context A. So we say that the context A can poison the branch predictor buffer and force a misprediction on this call on the context B. And then a thing called the Spectre gadget will be executed, and the Spectre gadget is nothing more than a piece of code that gets a secret and puts that secret into a side channel, for example, as you've seen with getEnv example. So we discovered that then we can actually call a function without calling a function. So we trick the CPU to calling a thing that it was never meant to be called in the first place. Other requirement for this kind of attack, but no longer more is a requirement, is that you need to have the address of a gadget right here. For example, if this whole program is randomized, we don't know where the function A should be to match the context B and jump to this address. So many places were saying that ASLR was a mitigation for Spectre, for Spectre V2. But in this talk, you're going to see that no, Spectre V2 is also a mechanism for bypassing ASLR. And then we can make a chain that we use Spectre V2 for bypassing ASLR and then to exploiting the Spectre V2. So we'll take a look quick in previous ASLR attacks. This is another paper that was published about exploiting branch targets buffer, but it was published before Spectre came out. So the guys that wrote the paper doesn't know about the impacts of mispredicting to other address. So it was used first to leak KSLR, that is kernel address randomization. It worked pretty fast for kernel, but also worked for leaking user-to-user ASLR, but at a rate of about 100 addresses being tested per second, which is pretty slow. If you check that ASLR randomizes like, I don't know, 12 to 40 bits, I don't know. That's a lot of addresses. That gives like 2 terabytes of address that can be, that's where when the program can be. And it only leaks the first half of the address because this mechanism of prediction, it cannot get the full 64-bit destination. So let's take an example for our proof of concept for Exec ASLR. Well, it's pretty simple. The requirements are minimal. We have right here a function that does nothing. We have a print for this pointer that's going to be randomized because of ASLR. We have a for loop that will, well, it's kind of cheating, but it helps us to know what value is going to be present on the branch history buffer. It's not necessary to be here because you can just debug the process that you are attacking and checking. Not debugging because it's going to be randomized, but you can check the patterns of the latest control flow instructions that change the branch history buffer, okay? And we're going to call the code pointer there. That's going to give us an indirect call. So the only requirement is to have an indirect call right there. And you know the 12 least significant bits because they're not randomized. And we test our attack in all Intel processors that we found on Google Cloud. That means 12, generation 2, 3, 4, 5, 6, 7. We don't know what happened on the 8 or 9, and it works on 10. But we have not tested on any more CPUs. And we're going to see that it's pretty fast. We initially called it reverse Spectre branch target injection. Because you the whole idea of this exploit is that in normal Spectre, you are trying to poison the victim program and forcing it to execute something. In our attack, we are letting the victim attack us using Spectre to then later recover the address that we're executing when mispredicting. This is the whole idea. We're doing a reverse Spectre. So this is what the memory looks like in our attack. We have a victim context running right here. It has a randomized address because of ASLR, and is calling constantly this function to here. And this creates a branch target buffer poisoning for our code with this address as a target. And then when we place a call instruction on the similar address, not exactly the same, it mispredicts to our thing here called leak gadget that is responsible to telling us, hey, I'm executing at this address. It does that using another auxiliary variable that is there, and it accesses this variable, and then this is a side channel attack that allows us to recover the address being executed. So let's take a look into what is this leak gadget. Well, this gadget receives two arguments. One is on CL register, and the other one is the actual probe array there. We're going to see how we're going to pass arguments for a function that we never call it. It's kind of strange saying that. But let's take a look at what it does. It takes the current address and move into array X. Then we select one of those bits chosen by the CL argument. We make an AND to make sure that it's the only bit present on the register. And we multiply it by 4096 or shift left 12. And then we access probe array at position 0 or 4096. And then we recover the using a side channel. We check, oh, what's the bit, the position 0 was the position 4096 that was accessed. So that's the idea. The idea is we have a victim code right there. We're going to try to mimic the last instructions that write to the branch history buffer. For example, that for loop, we'll try to mimic it there. And then we're going to place a call or a jump at the same address. The idea is that this one is going to call this address right here, and this one is going to mispredict to the same address. And then we're going to place our leak gadget there. So what's the challenge with this kind of exploit? Well, I told you that the whole range of ASLR, that is from this address to this one, if you make the count, it's going to be 2 terabytes of memory. We don't have 2 terabytes of memory for working with. Usually the computers only have like a 4 or 8 or 16. But we need to place this in all positions. So what can you do? First, we can use a copy on write. It's a thing used for reducing the space that you use for the physical memory by, if you have, for example, the libc. The libc is a great example. Many programs use libc. And they use the same exact version of libc. But the operational system says that, well, the process must have isolated memory because otherwise you could just read from other process. That won't be pretty smart. But the operational system also allows us to do copy and write. Or that means I can have only one copy of the libc on the physical memory, and then have multiple pointers pointing to that address. So, well, in this case, you could use, for example, in order to load 2 terabytes of virtual memory, create a file with like 1 gigabyte, and then trying to map that file, and then you can really have 2 terabytes of memory in your process. But we don't work with that, because I tried that the first time and it didn't work. Don't know exactly why. I think that many page entries on our process kind of doesn't work. And then we try something a little different. We only load one slice of 1 gigabyte, and then we use the syscall of remap to change the virtual address of that position. So therefore, we can try to test many. We can test one slice of 1 gigabyte per time, and then move on to the next slice and next slice, and then we have like try it 2,000 times. It's also pretty fast. Other challenge that we encounter on the exploiting is that in order to execute an address, it needs to be present on the TLB, that is the translation look-aside buffer. It's also a cache-like structure that stores the translations for the virtual address that you're trying to access on. The problem is that with those leak gadgets there, they're never going to get executed. So the address will never be on the TLB. So how can we put them on the TLB, or what are you going to do? The TLB is very limited in how much stuff you can put there. And doing a page walk is slow. So because we have to read from a pointer of change in order to calculate the physical address. So the gadget will never be called, because the page walk is slow, and then the speculation gets corrected before calling the gadget. So one idea we have is to increase the speculation window. So instead of just having a call brackets array x, for example, we're going to have a pointer chain that is going to have multiple pointers there, and finally on the last one, we're going to do the call. We also tried to play with transparent review pages, thinking that would decrease the pressure on the TLB. But what saved us was out-of-order execution, because this is what, no, next one. This is what the front end delivers to the rest of the pipeline. Well, you can see there, we have a pointer chain, and finally, we have the check that is actually a jump right there. And it also delivers these instructions that get speculated. But when getting into the reorder buffer, what the reorder buffer see is that we have a huge dependency of instructions that take too much time here, and they have some internal execution units available on the CPU, and this block here can be executed. And then what's actually going to be executed is this thing. So we have the loading of the arguments, then start to reading the pointer chain. We executed out of order or gadgets that's speculated, and it runs before even doing the actual call. So we learned how to call a function without calling a function, and before even calling a function. So this is our results. We have exploiting working for all Intel CPUs for N1 and 2. It takes less than 10 seconds per execution. Recovers all bits randomized by ASLR. If you force this time here, you get up to 1 trillion of address tested per second. But it's more like 100 billions per second. We also do it on a generation 10 CPU that it has a mitigation called single thread indirect branch prediction that says, oh, okay, you have a prediction unit for one thread and one for another. The idea is that it will be more difficult to exploit Spectre V2 across threads, but we don't care about that. So we just sleep and allow the scheduler to place the victim on the same thread that we are working on. Well, about mitigations, the great problem is how do we mitigate Spectre V2? No one's know yet. There's a mitigation available that can be done in kernel. It's also available no, I mean, it's already implemented, I believe. It's an indirect branch predictor barrier that is, the CPU allows for a special instruction to flush the prediction unit there, and then it should mitigate Spectre, but it's disabled by default because you need to do a syscall in your process to enable it. The other mitigation is a hardware mitigation that you can limit the amounts of bits predicted. For example, and they do it on the direct predictor. It only predicts to the 32 least significant bits. So that kind of reduces the impact of an attack like this. But it also implies on having some problems with performance, I believe. And like right now, it's time for the live demo. Okay. Okay. So we're setting the victim to run on the core 1. That's their address. That's randomized. You can see that each time executed, it's randomized. And then we're going to do our attacker. Oh, we'll get into that. Oh, it works. This address is equal to this address. Oops. Blah, blah, blah. I had a video, but don't need that. Oh. Questions? I promised a code review. I still have 8 minutes left, so I will open for questions, and then we can move on to the code review. That's my Twitter, blah, blah, blah. Questions and code review. I will open it. We can do it simultaneously. I lied a little bit about the victim code. We kind of hard-coded the for loop and the call. But it's still a for loop, and it's still a call. But I was having some trouble with aligning the instructions because the compiler was giving me like a call, RP plus blah, 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 and that instruction has, I believe, 8 bytes, and the call that I was using on the other process was only 2, and we have some trouble aligning those. But it should work. You can try it at home. Oh, you have a question? Yeah.
Yes. So you're forcing another process that's already looping to load into the cache the address that you're trying to leak. I guess my question would be is how tight of a loop does the victim process have to be executing in?
We tested it doesn't need to be a loop. It only needs to execute one time. We tried like the attacker signaling the victim process to execute it, and it also worked. We just need to have a little bit of a problem with scheduling, give it time to the signal to be handled and to get executed there. But it doesn't need to be a while loop like this one.
Well, I guess, so like in a real world attack, can you maybe, have you used this against like a service or a privileged process or something that?
No, not yet.
Okay. Okay, thanks.
If someone has any more questions, they can pass to the middle. There's a microphone there, or I can pass and give them the hand microphone. No one?
No. Can we do the code review?
Yes.
Okay. Well, let's go to the... No. Okay. This is the function of that program that you're trying to mimic. Right here, we have the for loop. Right here, we have the call. And we created a gadget that it's this thing called gadget clone that is actually these instructions. Right here, we have our pointer chain that works on, like you have just three pointers. Have the same for loop here. And what you're gonna do? We have an RDI pointer, very similar to the one on the victim. We have our probe array right here. We have a pointer chain here. They need to be spaced because otherwise you have some issues like trying to access a probe array and also accessing the pointer chain because they are near in the memory. We have our do nothing, some helpers for other functions. Have the probe here. It's the same function that I showed on the slides. It only gets a time a time of address in the memory. We have the call gadget here that only gets a few arguments. For example, the size of the loop, the index of the bit that we're trying to leak from the RIP. It passes the probe array here, and the destination, the pointer for the do nothing function there, and then it executes this gadget clone. Okay, this is how we call the gadget. We have a function called disclosure. I'm pretty bad at naming functions. We just flush the pointer chain, flush also the RDI pointer, use this CPU ID that is a special instruction that is usually for, well, it does many stuff, and because it does many stuff, people use it as a serializing instruction. It ensures that the flushes are actually executed and not doing something funny out of order. And then call gadget, passing the source of the code that we're trying to execute and the index. Finally, have the leak address. This is our leak gadget. This is the thing that you saw on the slide. We have an auxiliary variable for caching, blah, 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 blah. When we start mapping all the possible, well, I told you before that you need to match the 20 least significant bits of the source address in order to have a branch target buffer collision. So that's what we're going to do here. We're going to map all the, well, if you have 20 bits, 12 are not randomized, it remains 8 bits. We match all the possible positions for this one, and they are going to be here in the source page. Then we set up our pointer chain. This one is a little hack. It's a 1 GB page that I created just because it's faster to load it. It's created here. It only takes our leak gadget there and put it on this offset. And then you write it that many times into a file that is 1 GB. I believe you can also do it with a normal mmap and just copying the address there, but I was not having a lot of luck there. We are making sure that the destinations are present in the memory, or if in cache better. And then we start to moving that window of 1 GB across all the possible destinations using a memory remap. Have a funny print there. And then we'll do all the calls. We have calling that disclosure function that calls this thing here. This thing, well, it enters on this address, but we brute force this byte here. So it goes through all possibilities, and that ensures that we're going to have a branch target buffer collision. So then we later probe the probe array, and then we're going to check, well, was T1 fast? If T1 is fast, then a bit is 0. If T2 is fast, then a bit is 1, and I put it on this variable. Then we do a sleep to allow the process to execute. Blah, 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 blah. The other stuff just gets the time that took to execution. Let's try again. Let's try again with another address. Sometimes it doesn't work. It's normal, but it's working fine. I think our time is over. Any more doubts? Questions? No?
Yes, if there's more questions, no more questions? Well, so then we are going to give a big clap to our friend José.
Bien, a continuación le vamos a dar la bienvenida a Don Borgono y a Barrenuevo.